So here we talk about the magnetic field due to an arc. Okay, so here we have a circular arc of radius r, and then the central angle is phi. So the expression will look like this, and then we can actually use the Biot-Savart law here to actually derive this formula. Okay, so ds. Okay, so this is the arc, and then ds will be a tangent. It will be a tangent line to this arc, and then r is always the radius direction. So ds and r hat are always perpendicular to each other, which means this theta is always equal to 90 degree and sine of theta is equal to 1. So it will just you can just skip it. Okay, so all the other things you can put it outside, and then ds is actually this thing. So it is like okay, so this one is like r times integration of d phi prime from 0 to phi. So this thing is nothing but a phi, and then this r and this r square can be partly cancelled. So finally, we get this expression. And a special case of this is we consider the B field at the center of a full circle. So in such a way, we have phi equals 2 pi. Phi equals 2 pi. We'll get this. Okay. So the expression is a little bit different from the previous one. Here is mu 0 I over 2 pi r. This one is mu 0 I over 2 r only. Okay, but these two are totally different. Here we consider a circle of actually a ring. A loop, a current loop. Okay, a circular current loop. Okay, and then here we try to find the B field at this point. Okay, we have the B field at the center with the expression like this. And here we have a long straight wire, infinitely long, and then we consider the B field nearby. Okay. And just now we consider the cross product, using the right hand rule as ds crosses with r hat. Okay, so your thumb is pointing out of the page. And another way you use the right hand rule is like this is the current. And then you use your thumb follow you use your forefinger follow the direction of the current. Your thumb will point to the direction of the B field. Okay, so this is the other way you use the right hand rule to determine the direction of the B field. Okay, so here we have a quick sample problem. So this is pretty easy. So here the wire carries a current I and consists of a circular arc of radius r and central angle pi over 2 radian. And two straight sections whose extension intersect the center C of arc. What B field does the current produce as C? Okay, so for the first segment and the second segment, okay, actually this one will generate nothing at point C. Okay, the idea is like if you don't really sure, so you can try to apply the Biot-Savart law by yourself. Okay, so ds is something like this, and then this is actually the r, or the r hat actually points to the same direction. So in such a way, ds cross r hat will be a 0. And similar for this one, ds is pointing to the top right, and then this is the r hat direction. Okay, so in such a way, ds r hat have an angle of 180 degrees. So sine of 180 degrees is 0. So the segment 1 and segment 2 won't contribute to this B field. So the only B field it will contribute is so it is B is only mu 0 I over 4 pi r and then times phi is pi over 2. Okay, this is phi. So so it turns out to be mu 0 I and then over 8 R. Okay, so this is pretty easy. Just use the previous formula. And then here we have another one. So so here it says two long parallel wire carrying current I1, I2 in opposite direction. Okay, so this one. Okay, so this figure shows I1 is pointing out of the page, I2 is pointing into the page. Okay, so what are the magnitude and the direction of the net B field at point P? Actually, this point. Okay, so this is a right angle triangle. This side is R, and D, and then using the Pythagorean theorem, you can quickly know that this is actually square root of 2 times capital R. Okay, so assume the following value, I1, I2, and D. Okay. Okay, so here we have a B1. B1 generated by I1 will be mu 0 I over 2 pi R. And then B2 will be mu 0 I1, okay, I2 also over 2 pi R. Okay, so actually this one generates the B field at this point. Okay, of course using this equation, and then I2 also using this equation. Of course the direction of the B field generated at point P are different. Okay, so we need to discuss it further. Okay, and actually according to this one, D is a square root of 2 over R times R. So R is D over square root of 2. So this is nothing but 5.3 over square root of 2, which is 3.75 centimeter. Okay, centimeter. Okay, so here we already know the magnitude of B1 and B2. So here we try to understand the direction at point P. Okay, so here for I1, okay, you can use right hand rule to do so. So your use of thumb follow the direction of the current. Your forefinger will be something like this, counterclockwise. Okay, at point near I1. Okay, so in such a way, okay, you can somehow draw a circle like this. Okay, so over the whole circle, the magnitude of the B field will be this value, but at point P, it will be like this direction at B1. Okay, because the B field should be counterclockwise. Okay, so here we try to draw B1 here like this. And similarly for I2, okay, I2 is pointing into the page, so you use a thumb pointing into the page. Your finger will be like this, so the B field is actually clockwise. Okay. Okay. So B1. Okay. So it should be something like this. Over the whole circle, the magnitude of the B field should be this value, but at point P, okay, the B2 should be pointing to this direction, because the B2 over that circle should be clockwise. Okay, so here we have a B1 here and B2 here. Okay, so to find the B, okay, we need to add them together. So the total B should be B1 square plus B2 square, and then take the square root. So it will be mu 0 over 2 pi r, and then square root of I1 square plus I2 square, and then take the square root of the whole thing. So here we can plug in all the numbers. Mu 0 is 4 pi times 10 to negative 7, and then this is 2 pi. Okay, so 2 pi and 4 pi will be partly cancelled. This r is 3.775 or 0.0375 meter, and then square root of 15 square plus 32 square. Okay, so this is 180 mu Tesla. Okay, so this is the magnitude. Okay, because we already know this one and this one should be perpendicular to each other, so we will use the Pythagorean theorem to get the total magnitude, the magnitude of the overall B field. Okay, so here we can also find the angle. This is phi. Okay, this is phi, and then we also know that this is 45 degrees, so that we can add them together, so that we can answer the B field is how much degree compared with the positive x-axis. Okay, so this phi should be arctangent of this side is B1. Okay, this side is B1, this side is B2. So B1 over B2. Okay, B1 over B2 is this thing over this thing. Okay, mu 0, 2 pi r, all will be cancelled. So the remaining stuff is arctangent of I1 over I2. Okay, so this is arctangent 15 over 32. So the angle is 25.1 degree. 25.1 degree. So in such a way, theta, we consider this one to be the theta. Theta will be 5 plus 45 degree, which is 25.1 degree plus 45 degree, which is 70.1 degree. Okay, to the positive x-axis. Okay. Okay, so this is not difficult. So here we talk about the force between two parallel currents again. Force between two parallel currents again. So this is the extension to the content of the last chapter. So in the last chapter, we mentioned the second version of the Lorentz force as if we have current, okay, in an external B field, there will be force acting on this wire. So here we try to put two current together, okay, either parallel or so-called anti-parallel. Okay, so here it says parallel wires carrying current in the same direction attract each other. 就是两条平衡的电流，如果它们的方向是相同的话，它们会吸引。Okay, parallel wires carry current in opposite direction repel each other. 那如果它们的方向是相反的话，它们就会互相排斥。OK， 所以如果它们不是平衡的话，那你就要奋力，就是如果是刚好垂直的话没力，那如果是有一个角度的话，那你就要分就是看那个哪个分量它会作用在对方身上，就是这样。Okay, so for this case, we only consider the easiest case, which means if two wires are perfectly parallel to each other. So either the current is have the same directions or opposite directions. Okay, so the magnitude of the force on length L of either wire will be FBA will be this one.
Okay, so how do we get this? Okay, so here which we have FBA. FBA will be IB times L times BA. Okay, so BA means the B field generated by the wire A, generated by the wire A. Okay, so at the wire B, Okay, so so we consider this is the external B field when we consider the wire B. So in such a way, according to last chapter, the FBA, which means the force acting on B, wire B, due to the wire A, due to the B field generated by wire A, okay, will be FBA, which is related to the current, and then times the length, and then also times the external B field, which is here is a BA, okay, and then according to this chapter, BA will be mu 0 IA over 2 pi d. Okay, originally should be 2 pi r, but here the distance between them will be d. Okay, so mu 0 IA over 2 pi d, and then we plug this one here. So altogether we have mu 0 L, and then IAIB, okay, in the numerator, and the denominator we have 2 pi d. Okay, so we just substitute this one to here. It's okay. Okay, so here we also try to see the direction. Okay, so for the wire B, IB is from bottom left to top right. Okay, so L is in this direction. And then for the B field generated by A, okay, you use your finger. Okay, this IA, so your finger is pointing to that direction, and then your forefinger like this. Okay, so you expect the B field here is pointing downward. It is somehow like this. Okay, so this one and this one, something like this. Okay, so or maybe it should be something like that. Okay, like that. Okay, with the same height. Okay, so for this one will generate B field. Okay, suppose the current is going in that direction. The B field will be like this. Okay, so here will be pointing downward, something like that. Okay, so BA generated by this wire A will be pointing downward according to the right hand rule. So the force will be the force FB is I times L cross B. Okay, so L cross B, L is this direction, B is downward. So your finger, okay, so you use your finger pointing to that direction, cross it downward. Okay, so your thumb is pointing to the other way. Okay, so FBA pointing to that direction, and then if you're interested, you can try to also find that. Okay, so FAB will be pointing to the opposite direction. Okay, yeah, because L is like this, and then BB is like that. Okay, L cross B will be pointing to the opposite direction as FBA. So we can see that they are actually attracting each other. Okay, if they are opposite, if the current are in opposite direction, which means let's say IA is pointing to this side, IB is pointing to that side. Okay, so in that case, BA is still pointing downward, but L is like this. So L cross B should be like L cross B. Okay, so it will be pointing to that side. Okay. This is L. Okay, and then B. Okay, so yeah, so FAB and FBA. FBA will be pointing to the opposite side and show us FAB. Okay, F. Okay, so as FAB, so as FAB. Okay, so you can also see that. Okay, yeah. So the forces acting actually depends on whether the direction of these two currents are pointing to the same. If they point to the same directions, the wire will attract each other. Otherwise, they will repel each other. Okay, so here the general procedure for finding the force on the current I is to find the force on the current wire due to a second current wire. First, find the field to the actually this is just what we have done. Similarly, if two currents are anti-parallel, okay, so in the textbook it tried to call it like if they are parallel or anti-parallel, okay. If they are parallel, which means that the wire are parallel to each other and also the current are pointing to the same direction. For anti-parallel, it means that if the wire is parallel to each other and that the current of the two wires are pointing to the opposite directions. Okay, so actually in the textbook it tried to define the name like this, so that we don't repeat the wire parallel to each other and the current are pointing to the same direction or pointing to the opposite direction. Just use a single word to simplify the definition. Okay, so here we talk about something called the Ampere's law. So Ampere's law will be the second law in the Maxwell equation we learned. Okay, so in such a way, here the Ampere's law will be like this. Okay, it is actually like this. On the left side, it is a line integral. Okay, we will call it a line integral. 线积分 line integral 线积分 Okay, so on the right side it is mu0 times I enclosed. Okay, so the format is somehow similar to the Gauss law. For the Gauss law, it is like integration of E dot dA. Okay, although this is a surface integral, this is a line integral. Okay, and then here we have epsilon naught equals Q enclosed, which means we change this Q enclosed to I enclosed, and then change this epsilon naught to 1 over mu naught. Okay. Epsilon naught to 1 over mu naught. Okay, so 1 over mu naught on the left hand side will be mu naught on the right hand side. Okay, and then we also change Q enclosed to I enclosed. Okay, so they are somehow similar, and ds becomes dA. So I mean the other way around. Should be dA becomes ds. Okay, a surface integral turns to a line integral. Although it's not very rigorous in a mathematical sense, but in many cases, the formula for the E field and B field have some similar relationship. Okay, so here let's see how to understand this Ampere's law. Okay, so here we also have a definition called Ampere loop. somehow similar to the Gaussian surface. The Gaussian surface means closed surface. Okay, here the Ampere's loop. Okay, for the Ampere's law. Okay, so it also means the closed loop. Okay, so which means when we need to use the Ampere's law, we always need to define a closed loop first or an Ampere loop first. Okay, similar to when we want to apply the Gauss law, we need to have a Gaussian surface or a closed surface first. So let's say here we have an Ampere loop. We have an Ampere loop. Okay, and here we also assume that we have some current. I1, I2, and I3. Okay. Here it means that I1. Let me see. I1. Okay, this is a dot. Okay, this means that I1 is pointing out of the page, and then it is also a infinitely long wire. Okay, from negative infinity to infinity. Okay, so this is a wire, a long wire, okay, pointing out of the page. I2 is a long wire pointing into the page. I3 is a long wire pointing out of the page. So in such a way, the current enclosed by this loop will be I1 and I2 only. I3 is not enclosed by this Ampere loop. OK， 就是说类似Gauss law 的时候，我们考虑电荷就看它是不是被那个高斯面所包围着的。如果外面的话，我们就不算了。这个也类似，当你定义了这个回圈之后，有一个圈之后，那这个圈如果是包着这个线的话，它就算在内了。如果在外面的话，它就不算。Okay, so I1 and I2 count for the I enclosed, I3 doesn't count. Okay, so here we also need to consider the polarity. Okay, whether this is a positive current or a negative current. Okay, so for this loop, okay, assume that we try to consider the direction is counterclockwise. Actually, it's just up to you. You can either define it to be clockwise or counterclockwise. So everything will have a positive sign, or everything will have an additional negative sign. So the formula will still hold. What I mean is that here, if we define the current loop like this, okay, we have I1. We have I1 to be this way, okay. So using right hand rule, I1 is pointing out of the page, and then okay, it is following the direction. So I1 is positive, but here I2 is pointing into the page. It has the opposite direction for the loop as the loop. So which means that I2 will be a negative current. So this is how we try to determine the polarity of the current enclosed. Okay, so what I mean just now is that if we try to define the loop like this, okay, so in such a way, this current I1, we will consider it is a negative current. And then for this one, we will consider it to be a positive current. But in that way, integration of B dot ds always take a negative sign. So in such a way, this one is negative, which means all the terms multiply a -1. So all this -1 can be cancelled. So it refers to the same thing. Okay. So another point is how to understand what is this line integral. The Ri integral means that, okay, suppose we define the loop like this. Okay, we try to cut this loop into many segments. Let's say this one. Okay, this one. is ds. Okay, so ds is actually the tangent line to that loop, and then also follow the direction of the current. Okay, so in this way, the current is counterclockwise. So ds is pointing to the top right. Okay, and then if at this point the B field is pointing to this side, okay, we try to calculate B dot ds for this segment, okay, and also for all the segment, okay. For different point, the B dot ds may be different or maybe the same. It depends. Okay, but yeah, generally it may not be the same. Okay, so in such a way we try to cut the loop into many segments and then try to compute B dot ds for every segment, and then this dot product become a scalar, and then we add all these scalar together. So finally, if we add all these B dot ds together, it becomes this line integral. So originally, a line integral doesn't necessarily to be closed. So maybe sometimes we can have something like this. So this integral is not for a closed loop or an amperage loop. But if it is an amperage loop, similar to the Gauss law, if it is for closed surface, we draw a circle here to specify that this line integral is for a closed loop or an amperage loop. OK， 所以如果理解高斯定律的话，理解这个的话，应该会比较容易了哈，应该会比较容易。Okay, so here we have something like this. So we can use the Ampere's law to find the B field of a long straight wire with the current. Okay, which is what we have done previously. For this part. Okay, so actually we can use the Ampere's law to derive it again, but we can also derive some other result. Here, what we try to consider is that we have a wire like this with a small radius. This radius is actually capital R. Okay, it's actually capital R for the radius of the wire. Okay, previously when we mentioned that okay, we assume that the wire is very long and very thin. Okay, the radius is perfectly zero. But here we assume that the current here is the wire here has a radius of capital R, and then the current density is uniform over this cross section. So in such a way, we can use Gauss law, the Ampere's law to find this one. Okay, so actually we have integration of B dot ds equals mu 0 I enclosed. So here mu 0 I enclosed is nothing but I. Okay, and then for this one, okay, we can actually find that for every ds, B has the same direction as ds. So which means that B dot ds becomes B times ds, and then times cosine of 0 degree. Cosine of 0 degree is 1. So yeah, because cosine of theta, cosine of theta is 1. Okay, so this line integral becomes something like this, B times ds. And we can also find that due to symmetry, B will be uniform over the whole loop. So which means we can put this B outside, so we have an integration of ds equals mu 0 I. Okay, so this is nothing but the circumference of this Ampere loop, which is 2 pi r. So we have B times 2 pi r equals mu 0 I. And then we can get B equals mu 0 I over 2 pi R. Okay, so this one should be small r rather than capital R. Okay, so this one is for this case. Okay, but here we can also derive another interesting result. So it is actually the B field inside the straight wire. So for B field inside the straight wire, okay, we can have another case like this is the wire, and then this will be the Amperean loop. Okay, so with a radius of small r. Okay, so for this part will be the I enclosed. So I enclosed divided by pi r square will be the total I divided by the pi capital R square. Okay, because this one will be the current density, and then this one will also be the current density for the whole wire. Okay, this is the current density within the Amperean loop. Okay, so they should be equal to each other because we assume the current density are uniform over the cross section. So in such a way, we have a I enclosed equals I times R square over capital R square. So in such a way, we have an integration of B dot ds equals mu 0 I enclosed, which is mu 0 I times R square over capital R square. And for the left hand side, it will be similar to this case, so which means we have B times 2 pi R equals mu 0 I times R square over capital R square. So R and R square can be cancelled. So we have B equals mu 0 I small r over 2 pi capital R, which is R capital R square, something like this. So this is this one. This is this one. Okay, similar to what we done in chapter 23. In chapter 23, we also assume a case, we have a sphere with a uniform charge density. So out of the sphere, we can have an expression similar to a point charge. In this case, like a long straight wire and long straight thin wire. But inside it, we can obtain another expression which is linearly increased. Okay, so both of them are similar to each other.